by the way, so don't rely on the recording. But hopefully it will work. The problem with that is this system, it's this box here, right? And it's these are newish systems. They're quite expensive, but they're still a bit flaky. And one of the problems that occurred last year is it's very difficult to get the recording level right, and there's no indicator on the box of what the recording level is. So when you hear this played back, it might be going, no indication on the box what the recording level is. And then you have to turn up your computer and you'll just about hear me. If it is recording, which is no guarantee of. But it seems worth trying. Okay. So maximum likelihood. I think this effect also, this weird effect on the screen is also the box. I'm going to try and fix that across next week. So the question is, well, we've got these distributions that we want to represent what's going on in the world. So the model that I'm proposing for machine learning, and it's not the way everyone does it, but is that the world is some vast probability distribution with everything correlated, or not correlated as the case may be. The butterfly in China causing the thunderstorm in Basingstoke. So that's the idea. So there's some interrelation between all these variables, and if you can model that probabilistically, you can make predictions. You can use these rules of probability to condition. What's the probability of a thunderstorm in Basingstoke given a butterfly in China? Well, you don't get any information from that, but that's the general idea. Some vast probability distribution modeling the entire world. Although in practice, we can't typically do that, so we have something simpler with a little deterministic component and a probabilistic component. But we need to be able to fit this distribution to data, because we don't know this probability distribution that governs the world. Just like we don't know what's governing your heights in terms of all its mechanisms. Maxwell could derive it for something simple like air, well, helium under a low pressure state. But for most situations, we can't derive the probability distributions. We have to estimate them. And the way we do that, well, one way of doing it is something called maximum likelihood. And I'm going to motivate it through an entropic approach, which is actually an information theory approach. So that last thing we talked about, the negative log of a probability, which we said was like the information. Turns out the expectation of that negative log of a probability. So the way to view this is it's an expectation because minus log of p of x is a function of x, right? Because p of x is, in this case, a functional probability distribution. So that's an f of x. It's just a particular type of f of x. Minus log p of x. Then we're summing it over p of x. So it's an expectation, yeah? So this is an expectation, and it's a particular expectation that we call entropy. Entropy is a wonderful thing. In physics, Boltzmann explained how entropy, and his entropy was related to this one, but you can show that they're equivalent. Entropy explains why some processes in physics aren't time reversible. Remember when I showed you those billiards last time, and we started off with constantly moving billiards at some constant speed that bumped into a wall on the other side and then reverberated, and they all had constant speed, but because of slightly different initial north-south directions, they eventually started bumping into each other, and as part of these collisions, the speeds started to become distributed in a Gaussian form. Is this what I'm saying?
Is FF110?
No, I think this is lecture theatre 10.
Sorry.
All right. It's going to be useful on the video, that. Entropy, so variance is one way we could try and measure that uncertainty, but actually if we looked at the variance in that case, we would have found that the variance of that distribution was the same because the energy stayed the same, and the variance in that case happens to be related to the energy. Entropy is a much more interesting measure of that uncertainty. What went on there is we went from a low entropy state to a high entropy state. And that's called, in physics, the second law of thermodynamics, that will always happen. It's a beautiful law because it's not even a physical law. It's a consequence of mathematics and statistics that these things happen. It's not down to physics, it's just a consequence of maths. That in those sort of situations, uncertainty, disorder will tend to increase, entropy will tend to increase. And this particular expectation is a measure of the disorder of a distribution. Yeah? Why is it a measure of disorder of the distribution? Well, if this is a discrete distribution, like that example we had before, where 0, 1, 2, and we put all the mass on 1, so the probability of age 0 is 0, the probability of age 1 is 1, the probability of age 2 is 0. Yeah? If we look at this sum here, what we get is, for the first example, at 0, we get the sum of 0 log 0. Does anyone know what 0 log 0 is? 0. Thank you, yeah. You have to prove that because log 0 is actually minus infinity, and 0 is, the question is, does that go to infinity faster than 0 goes to 0? And the answer is no. So 0 log 0 is 0. So 0 log 0 is 0 plus 1 log 1. What's 1 times log 1?
1.
Is it?
0.
0. Log of 1 is 0. So we've got 0 again. And 0 log 0 is 0. So the entropy of that is 0. There's no uncertainty in that distribution. You maximize the uncertainty in distribution by making it a uniform distribution. So that would be a third times log third multiplied by 3 times. And that turns out to be the maximum you can get. Yeah? That's fully uncertain. Uniform distribution. Okay? Now, that's the entropy. But what we need for maximum likelihood is actually this thing called the cross entropy. Okay. It's a special type of expectation. And it gives us the measure of difference between two distributions. And this is something we're interested in. Why are we interested in this? Because if P of x was, for example, the real world that we didn't know, and Q of x was our approximation to the real world, we might be able to use this, not quite clear how, but that's what we're going to show, to push our approximation to the real world closer to the real world, P of x. Yeah? So if P of x is the real world, this is a measure of divergence between two distributions. So as these distributions get more different from each other, this thing goes up. If they're the same, it's 0. Now, why is that obvious that it's 0? That should be a P of x that's just fallen off the screen there, I'm afraid. If they're the same distribution, then this is equal to, well, look on this side, log of P of x over P of x. P of x divided by P of x is 1. Log of 1 is
0.
Expectation of 0 under P of x? 0. Yeah? So it's 0 if they're the same. And you can also see that if you write it in this other form, because this is the entropy, sorry, the negative entropy of P of x, and this is the expectation of log Q of x under P of x. And if that was P of x, then these two things would be the same, 0. And it's positive if they are different. So it's less obvious that this is true, but that is the case. That as you make these two distributions different, P of x and Q of x, this KL divergence, Kullback-Leiber divergence, sometimes called cross entropy, goes up. It's an information theoretic measure. Now I want to just illustrate this by showing two Gaussian densities. So in the cyan density is Q of x, and our real world density is P of x. And what we can do is analytically compute this measure between the two. And I'm just going to vary some parameters of the cyan. Yeah? And as we vary the parameters of the cyan, I'll plot on the right-hand side what this KL divergence is doing. So initially, I'm making the variance of the cyan. The means are the same, yeah, here? But I'm making the variance match. At the point at which the variance matches, the KL divergence between the two distributions is 0. So, as they don't match, this measure's going up, yeah? And then what I'm going to do is I'm going to move it to the right and simultaneously increase the mean. And that increases the KL divergence again. So, I mean, that's a MATLAB proof. It's not any kind of proof, but it's just sort of using a simulation to show how KL divergence can vary. Yeah, so as we move these distributions, make them less similar, the KL divergence goes up. Okay? Makes sense? So if we had the real world was P of x, and we wanted to derive a Q of x, which represented our picture on the real world, we might be able to use this KL divergence to help out. So that's what this side says. Now in practice, we don't know the real world. Yeah? We only have samples from it. You are samples from the real world. So if we're trying to model your heights, we don't know the real world distribution. What we do have is the observation of what your actual heights are. So that's samples from P of x. And what we're going to do is use a sample-based approximation to the KL divergence. So the sample-based approximation to the KL divergence looks like this. Those expectations we had before are now replaced with the sum over the f of x. Remember, this is f of x again, yeah? So it's replaced with the sum over f of x. Does that make sense? Any questions there?
I have a question. Why this is always positive?
Why is it always positive? You can show it's always, I mean, it's positive because of the math. The way you prove it's always positive is with something called Jensen's inequality. So that's a quality of, an inequality of, I don't want to show it to you because I don't want you to, the things I show you, I want you to be able to recreate in an exam. So I don't want to show you that proof because I don't want you to recreate that in an exam. But the reason is that you can show it's the case through Jensen's inequality, which is an inequality that relates the expectation of a log to the log of an expectation. And using that, you can show it always has to be positive. But it's just a consequence of the maths. Is that, it's not a clear answer, because I don't want you to have to try and reproduce it. But it's called Jensen's inequality, the bound that you use for that. And I think it's in Bishop. It's in the textbook, if you're interested in seeing it. But I don't want to put it in the slides, because the stuff I want in the slides is stuff that I expect to be reproducible, yeah? Okay, so it's in the book. Problem, we've still got P of x. Yeah? And that's what we said we didn't know. That's the world distribution that we're trying to approximate. But this term doesn't depend on Q of x at all. In the sum, you've got this P of x and this Q of x. Yeah? So the only term in this thing, if we want to minimize this thing, the only part that depends on the Q of x we're interested in is this part. This part is the negative entropy of the world distribution, but it doesn't matter. Yeah?
Please can you help us with an example of this, because it's a bit too abstract.
Yeah. This is an example. Okay. So back to an example of the sample-based thing. Yeah, that's what we're leading to with maximum likelihood. Yeah. So this is supposed to be an example showing how these things differ. Are you happy with this example representing this version of the formula? Yeah. So, and the reason we can go from this version of the formula to this version of the formula is because of a sample-based approximation. So I haven't then given an example of this, but in fact, most of the next bit of the course is really examples of this. I'm motivating this. This is the statistical or the information theoretic justification for maximum likelihood, right? This is not something you have to reproduce every time you derive maximum likelihood, but it motivates why maximum likelihood works. Okay? So you can't compute that, but you can compute this. Okay? It's known as the negative log likelihood. Negative, because there's a minus sign, and log likelihood we'll come on to in a minute. But what it is take the samples you're given. This is your distribution of interest. And the thing you want to minimize is the sum over those samples. Doesn't matter whether the one of n's there or not. That doesn't affect anything. It's just a scale. We can take that out, and typically you do take it out. But minimize the negative sum of the log of the distribution evaluated at those samples. That's what this says we should do. Got a funny little error. So minimizing the sample-based KL divergence is equivalent to maximizing the likelihood. So what do I mean by that? Well, there's a negative in it, so minimizing this is equivalent to maximizing the positive. Now, I'm going to try and stick to a convention. We normally do maximum likelihood, yeah? And so you typically maximize things. But in the field of optimization, they always talk about minimizing. It's just a convention. So you need a convention because otherwise you can't. So there's a field called convex optimization, right? So a convex function is one that's shaped like that. Yeah? Convex optimization means that there's only one minima. It only makes sense to call it convex optimization if it's minimization, not if it's maximization. The way you turn minimization into maximization is by flipping a sign. Yeah? So although we do maximum likelihood, the tradition in the field of optimization is to minimize. So we actually do minimum negative log likelihood. Yeah? So that's just a side issue. It's called maximum likelihood, but I'm going to try and stick with the idea of minimizing a negative likelihood, just because that's what they do in optimization. And that's what we have to turn to do this. To minimize this function, and its minimum KL divergence, which is maximum likelihood because of the negative sign, we have to turn to optimization. So it's unfortunate there. This is just supposed to say P of x given theta. So this is what we call the likelihood. So the probability of the data given the parameters of the model is the likelihood. And that's what we want to maximize with respect to the parameters. So this is how we change the nature of the distribution. So maximizing likelihood is equivalent. Okay. Another point is, what does the logarithm do? So we've talked about maximizing likelihood. We're saying maximum likelihood. This is the likelihood. So it should be P or Q of x we can even think of. In fact, you know, this term here is really containing the likelihood. What's the log doing here? That's also important, and important to get that lesson in your head early on. Maximizing log likelihood is equivalent to maximizing likelihood because log is a monotonic function. Now I'm going to show a little example of that. So here y is log x. Log is a monotonic function. It goes continuously upward. Yeah? So which is the largest x? It's the x10 in these examples of these different arrows. Yeah? Which is the largest y, where y is equal to log x. It's the same, it's log 10. Yeah? Because log is a monotonic function. So if you take any function and you apply a monotonic transformation, maximization of that function, the maximum point stays the same, if the transformation is monotonic. If the transformation isn't monotonic, so it's not continuously going upwards like this quadratic here, then the maximum x is not necessarily the maximum y. Because this small y here has now been allowed to go above x, right? You get the point there? So if I maximize a function, I can always maximize its logarithm, or the log of its logarithm, or the log of the log of the log of the log of the logarithm. I can do that. Any monotonic function that's true for. Logarithm will turn out to be really convenient. This is the likelihood. The probability of the data given the parameters. This, in a Gaussian case, this would be the probability of all the data that we've observed, x, given the mean and the variance. And what we're trying to do is maximize that probability with respect to the mean and the variance. But this isn't quite the form. So I've moved from P to Q here. Q is the approximating distribution here. It's not quite that form, is it? Something wrong. And I just want to show what that wrong thing is. So this is a joint distribution, P of x, over all your heights, given the mean and variance. So we're assuming in here somehow that the heights could be correlated, given the mean and variance. This is a joint distribution. But typically, a simple assumption is to not assume that. To assume that it doesn't matter which individual we're looking at, that your height is drawn from the same distribution. Now that might not be true. Why might that not be true? Because you could be from different nations, different cultures, which have different average heights. Yeah? Or you could be different, or gender. According to gender, you have different heights. But we're going to assume that that's true. Now, under that assumption, this joint distribution over all heights, which this is a multivariate distribution, so it needs to specify the correlation between your height and your height, yeah? Or your height and your height. It needs to specify all that. It has to have all those parameters in.
Kind of strange question. So you're talking about the likelihood. The likelihood, are you saying the likelihood that the probability distribution is the specific kind of distribution? What's likely? Is it like the likelihood?
You have to be very careful when taking a scientific name and relating it, or a technical name, and relating it to what it means in real English.
Right.
Because even if someone named it sensibly at the beginning,
so like real numbers, for example.
Yeah. Well, they are real. No, okay. Yes. Well, the meaning of heat in physics is a specific thing. It's an energy thing. It's not necessarily, it doesn't mean the temperature. I mean, it's related to the temperature. So, can we map the word likelihood onto what it means in the English language? No, I'm not sure we can. I don't tend to think of it like that. I just think of it as a term for that probability distribution. The probability distribution of your data given your parameters. And it could also be given your inputs as well, by the way. So it could be given the parameters and some piece of information about you, like your gender or your nationality or your age or whatever, or the temperature in this room. Could be that as well. But in this case, we're just saying the probability of the data given the parameters. And then if we've got samples, observations of you, then they can go into the model. So we've got each individual. And what this part is saying is that it's independent across data points. So this is a mapping from, let's turn the lights on for a moment and use the board for a bit. So what we said before is P of x comma y is equal to P of x P of y if they're independent, yeah? That was the independence assumption. Here the independence assumption is being written in vector form. The P of x here is a vector x. This is how you're going to represent things when you do the lab. You put all your data in a vector or something. So this vector is, I don't know, there's 30 students in here. It's 30 different values of height. So it's really P of x1, comma x2, comma x3, comma x4, where each of you has a number. Yeah? and it's your height. That's what this is saying. P of x, where x is a vector. So the fact that it's in bold means it's a vector. And then that's given the parameters, which we use theta for parameters very often, but the parameter set is the mean and the variance or whatever other parameters are in the model. Now, this assumption of independence across data points means we can rewrite that as P of x, or P of x, comma x1, comma x2, is equal to P of x1 times P of x2 times P of x3 times P of x4, yeah? In each case, I'm missing out the parameter set. So really that should be P of x1 given theta, P of x2 given theta. So the parameters are the same in every case, x3 given theta, P of x4 given theta, so on and so forth. Now, as you probably can imagine, it's quite tedious to write that all the way out, so of course we just use the product sign across the data set. Yeah? So the probability of the data given the parameters is the product of the individual data points given their parameters. It's an independence assumption. It's not necessarily true, and indeed, when we do a little bit of Bayesian stuff in week 4, I like to think of it as, well, I'd like to say that typically it's the assumption we're putting on this portion of the model. Yeah? If everything was completely independent, we wouldn't learn anything about it, right? So things are actually being correlated by this portion of the model, yeah? The parameter version of the model that says that there's a relationship between you, that your height is related to your weight or something like that, yeah? And in this case, here, the noise corruption is really what we typically put the independence assumption on in machine learning. But in general, when we're doing maximum likelihood, it's just an independence assumption for the data. Now the point is, we've said this is the likelihood, right? But we said that the log likelihood, maximizing the log likelihood, is the same as maximizing the likelihood. Now one motivation for the log likelihood is the KL divergence sort of sketched proof we gave. But here's a much more practical reason. You're going to have to maximize this function with respect to the parameters. You want to know the most probable set of parameters, the parameters that make this data most probable. That's another way of looking at it. So that's maybe where the likelihood comes in. You're looking to find the set of parameters that make this distribution most probable, yeah? You want to maximize it. How do you maximize things? What's the first step you do when you maximize things? Do I hear something? Yes, that would be true. Yeah, take the negative to minimize. But regardless, even if we're then minimizing, the next step is, how do you find a maxima or a minima?
Differentiate.
Differentiate. In fact, you normally differentiate twice when you're looking at a one-dimensional function. You differentiate once and try and find a point where it's 0. Yeah? And then you may differentiate a second time to prove that that's a maxima or a minima. Yeah? So the first thing you're going to need to do is differentiate. If you differentiate a product of things, you typically find that's quite awkward, because you have to use the product rule of differentiation. Not the product, is that the product rule of differentiation? Well, you have to basically, you end up differentiating each term individually, keeping the others held. And it leads to a real mess. Yeah? But how can you make your life a hell of a lot easier? Apply a logarithm, and that product becomes a sum. So each one of these terms involves theta, right, in this product. So you have to sort of I think, well, I can't even remember how it goes. I do know them. But basically, you'd have to differentiate the first term, holding all other n-1 terms fixed, then differentiate the second, holding the others, and then you'd have to combine them all together. Yeah, a bit of a mess. If you take the logarithm, you just get the sum. The product becomes a sum over the individual log likelihoods. And the gradient with respect to each term of the sum is the same. Yeah, because you can differentiate each sum in term. So it's a really sensible thing to do, to take the logarithm of this product before you take the gradient. There's many other motivations why you tend to maximize the log likelihood that I think would come from just an optimization perspective, why it may be a good idea. But there's a couple. So what we've got the form of this, what I've written as L of theta, which is one way of writing the likelihood. Because importantly, we're maximizing the likelihood or the probability of the data given the parameters by optimizing the parameters. So this is a function of the parameters. Yeah? So when we write L of theta, we're saying it's a function of the parameters because that's what we're trying to maximize. Or we're trying to minimize the negative log likelihood. So the difference between this likelihood, log likelihood, and the thing we saw before is a scale of minus n. So in practice, what we typically do is we minimize minus the sum of the log likelihood and we ignore n. Now, it would be great, wouldn't it, if we knew when we had the right answer because this whole thing was equal to 0. But it's never going to be equal to 0 because you don't know what this term was. This term is the negative entropy of the real distribution. So you'll never see that. So you don't know what this term, at a minima, this term should match that term at the global minima. But you don't know that term, so you won't see that. Problem 1. Problem 2, this approximation, or I mean this true thing here, is only 0 if your density Q of x is in the same class, well, contains within it P of x as a special case. That's a big ask. So the family of densities we're using for height, Gaussian, is our Q of x. We're somehow saying that your heights were genuinely distributed as a Gaussian somehow. Yeah? They won't be. There'll be some non-Gaussian thing to them. So this proof I've given you is the justification of maximum likelihood, yeah? And it says that it's globally optimal under 2 conditions. Condition 1, in the limit of infinite samples, because that's when these sample-based approximations become correct, yeah? In the limit of infinite samples. Condition 2, if Q of x contains within it the space you're optimizing over P of x as a special case. So you have to have a general enough class of distributions that the true data is going to be a special case of that. Are either of those conditions reasonable? No. They're both stupid. The first one is stupid because no one has ever given me infinite data. And if they did give me infinite data, I wouldn't know what to do with it because I don't have enough computational power. The second one is kind of stupid as well because it's very unlikely that whatever density we make up is going to be more complex than the way the world works. Yeah? The world's typically going to be more complex than our data. And in fact, if we do come up with a very complex density here, then we'll tend to overfit something that we'll see later. We'll tend to become too clever about what we think is going on. So, is this proof that I've sketched out useful? Well, maybe not. I don't know. But it certainly justifies looking at maximum likelihood as an approach. In statistics, there's been a lot of work studying proving that a method is consistent. That means showing that as the data goes to infinite data, you do recover the correct model if it's within your class. So maximum likelihood is consistent. If your method wasn't consistent, that might be a worrying thing. But in practice, you never get infinite data, so it perhaps is not so important. The other thing people might look at is the rate of convergence. And the rate of convergence is the question, how much data do you have to have? How big does n have to be before you start getting towards the truth? In machine learning, people also worry about those things. We're not going to touch on them in this module. So the properties of maximum likelihood arise from this explanation of the KL divergence. That as n goes to infinity, if the class of distributions considered for q of x contains p of x, then we will obtain q of x equals p of x, yeah? We'll get the right answer. This is known as the consistency of maximum likelihood. And in practice, though, we won't have infinite data, and we can't prove that q of x will contain p of x as a special case, unless we generated the data ourselves from a known p of x, which is something we can do. So to maximize the likelihood, we use optimization techniques. And in the optimization community, minimization is the convention. So we define the error function as a convention to be the negative log likelihood. Now, because that means then you're minimizing an error. And very often you'll hear people talk about machine learning algorithms as minimizing an error function. Now, you might have an error function that isn't a negative log likelihood, whatever. You could make up your own error function. And E can also be thought of as an energy function. In physics, that's often the way they represent probability distributions. They represent it by the energy function and the partition function. The partition function is the normalizer of the probability distribution. So we'll just use E. And what we're going to do is try and minimize E of theta. So to find a minimum, we need to find a point where the gradient is 0. That's a stationary point. And then if we can show the curvature is positive, then that's a minimum. So the procedure for maximum likelihood is to differentiate the likelihood function and find parameters which set the derivative to 0. Yeah? So sometimes that can be done by a fixed point equation. So in some nice cases, the Gaussian fit being one of them, and linear regression being another that we're going to look at, you get a fixed point equation. What that means is that when you set the gradient to 0, you get a formula which you can immediately find the solution. So you can jump straight to the solution. The reason they work is because the log of a Gaussian has what kind of form? Do you guys remember what the Gaussian looked like and what the log would look like? Yeah, well, it would look like a bump, but functionally, the Gaussian was exponential of minus what sort of form? It's a sort of what we'd call a quadratic form. So this goes back to, I remember someone did mention least squares last lecture, and you'll start to see the relation as we develop this. The Gaussian has this form. Okay, I'm missing the partition over here, but let's ignore that because in the log, any product is just a constant will move out. So I'm caring about this form. Yeah? So you're going to have to really remember this. What's the log of that? Come on. Very good, Alan. Log is the inverse of exponential. What kind of easy, simple form is that? Well, it's a quadratic. When you differentiate quadratics, what do you get? Straight lines, linear functions. That means that when you look at the minima of quadratics, you can find them very quickly. Minimizing a quadratic function, these likelihoods turn into quadratic minimization problems. Quadratic minimization problems without constraints are trivial. Yeah? As will, I mean, you won't think that they look trivial, but compared to other minimization problems of really nasty functions, they're trivial. So it's also, because of the sum, it's log likelihood sum, you can start seeing, and negative, yeah? Let's ignore sigma for the moment. Sum of the squared error. Maximum likelihood of a Gaussian minimizes the squared errors. Yeah? It's the correct interpretation of minimizing squared errors, according to me. Some people like to think of that as a loss, but it's the way Gauss derived it, and it's very explicit about what you're saying. What you're saying is that the error is a corruption by a Gaussian distribution. That's what you're saying. Okay? So, the next thing is maximum likelihood in a Gaussian. I want you to do this. It's in Bishop as an exercise for next Tuesday. Yeah? You may not be able to get all the way through it, but I want you to have a look and a think about it. What you've got to do is you've got to take the log of this function, which makes it a sum over n. Yeah? And removes the exponential. Takes this ugly looking function and turns it into something really simple. And then I want you to think about taking the gradient of that, certainly with respect to mu. Yeah? Don't worry, let's not worry perhaps about sigma. For next time I want you to worry about taking the gradient, because this term doesn't depend on mu, yeah, so that we can ignore that. It does depend on sigma. And actually, since sigma's a scale, it doesn't affect this. It comes out the front like that 1 over n. So it's a 1 over n, n sigma squared, if we included the 1 over n. But you can just ignore all that. This is the baby that you need to differentiate. So I want you to think about differentiating that and solving it for mu. The maximum likelihood solution for the mean of a Gaussian. Does anyone have any idea what form that should take? Have a think about it. What form should the mean take as a function of the data? So this is going to be a sum, I equals 1 to n. This is the function you're trying to minimize to get the maximum likelihood. It's minimized because I've taken the negative out, yeah? So take the gradient, and then you could also look at the second derivative. It's an exercise in Bishop as well, or there are details in Bishop. So I want you to think about that for next time, okay? Sorry, let me just switch the recording off.
We still cannot access the
Yeah, someone mentioned that. Yeah, I'll try and fix that.
Okay.